I never thought that we would be talking about the Monty Hall problem so many years, 40 years, after it had first been proposed. I thought everything that could possibly be said about it has been said about it. And yet my friend Alex came up with a solution that was so easy to understand that it's almost a philosophical proof. It doesn't involve any numbers. I thought I would share it with you. So here goes. Now you probably know what the Monty Hall problem is. You've got 3 doors and behind one of them is $1 million prize. And you choose one and then the organiser takes away one of the remaining 2 doors and then gives you the opportunity to switch. So the question is it better to switch or is it better to stick with your original door? Now the answer is that it's always better to switch, but trying to understand why it's always better to switch is quite complicated. It's a complicated calculation. It involves probabilistic calculations. You can analyse it with something called Bayes' theorem, and it's counterintuitive. Now, to understand why it's better to switch, all that you have to do is imagine there are more doors. So this time, imagine there are 1,000 doors, but everything else remains the same. So you choose one of the doors, and then the organiser takes away all but one of the remaining doors, and this time, are you better to switch? And it should be easier to see that you were very unlikely to choose the $1 million prize door first time, and therefore it's highly likely that the $1 million prize was within the remaining doors, and when the experimenter has taken away all the doors that don't have the prize, you are left with almost certainly the one that does. And that's all there is to it. If you want numbers on this, your chances of choosing the $1 million prize first time are 1 in 1,000, and the chances that the prize is left in the remaining doors is 999 in 1,000, and that doesn't change when the organiser takes away all the incorrect doors. So you know that expression 9 times out of 10 or 99 times out of 100? Well, this is 999 times out of 1,000. You're better off switching. And there it is, the Monty Hall problem.